Okay, so welcome to the channel. So today we're going to learn how to use LTspice with the Mac. This is the Mac edition, which is definitely different than the PC edition. And we're going to just go ahead and just jump into it. So we're going to be working on this particular circuit here. We have a 12 volt source, a 36 volt source, and a dependent source, which has at the 5 kilo ohms a negative positive Vx, and then the dependent source itself on the top, which is the 2Vx. And the idea is that when you go through this, I'm putting in the voltage sources first, as you learned in the previous videos, and we're going to include the resistors as well. So I'm just recreating this exact pattern that you see in front of you. And with the LTspice, it's hopefully relatively okay with the Mac so far. To make things rotate, you hit the Command R or Control R button, and it actually rotates about. And here's the important piece: is when I actually add in the voltage dependent voltage source to the actual problem, or just hit the E key. So I'm going to rotate this around so that it matches the exact dependent source that we have over the 2Vx. Hit escape to get out of that. And now, of course, that we have the basic components out of the way, the important thing now is to include the wires. So we can just go ahead and wire and connect it from one component to the other. Sometimes this is easy, sometimes it's a little bit frustrating depending on how comfortable you are using your mouse. And of course, clicking on the ends, you have to make sure that you're precise with that. But overall, it's hopefully not too bad. As you go around each one, like I said, it's really up to how you like to do it, but I like to generally put all my components in first and then attach all of the wires to my circuit. So now that I have that, you have multiple options you can do next. You could certainly put in the ground, and if you don't put in the ground, I also love to label or at least enter my values for each component. You left clicked on each component, right click on each component, and you make sure you're entering in the source voltage, for example, DC voltage source, and not changing the actual name of the component itself. So again, I'm replicating what we have here. What's nice about LTspice, you don't have to write in 10,000. You could literally put in 10K and 5K to represent the resistance in ohms for each of the resistors that we have here. Okay, so there it goes. So once you have that, we're basically set or close to being set. So notice now I'm going into our voltage control and I'm changing the value. Why again? Because the gain, which is our multiplying factor, is a factor of 2 for this dependent source. So what is it dependent again on is a 5K ohm resistor. I go over the math and the actual problem solving. That's if you hang tight for the next few minutes. I'll certainly go over that as well. But what's important is that you have the polarities correct. So if you have the positive end of your voltage dependent source is connected to the positive terminal, which is on the right side of the 5 kilo ohms, and the negative of my dependent source has to go to the left of the Vx, or aka the 5 kilo ohm resistor. So from there you go to the net name, include a ground to this. The ground can go certainly anywhere, but it makes more sense in this case to put it towards the left where I just placed it. From there, you always want to include how long you want to run this simulation for. So I run it for 1,000 seconds. Usually what I do for most DC problems, just out of convention. Sometimes if you run this, it says missing gain values, make sure you put it in there, go back to value, hit enter, and then OK to ensure that it goes through, and then run it again. And just like that, we should have now the image here. So now we can take a look at the currents of the circuit. It's a series circuit, which means we expect the current to be the same everywhere. And we're also going to check a look at the voltage. And what we're expecting is that the voltage, well, first let's look at the current. The current's 0.8 milliamps. Right, I'm checking at 10K, I'm checking the current at the 5K, I'm checking the current at the sources, and they're all should be reading the 0.8 milliamp. Okay, as you go through it, and more importantly, now we have to also look at the voltage. And what we're expecting for our voltage is that there should be a 2-to-1 ratio, because on the bottom, the Vx, as you can see here, I'm getting this 4 volts, so technically minus 4 volts with the simulation. And then if you look at the top node for our dependent source, and I check the voltage there, right? I'm probing it from one side to the other by holding down the left click button, I'm getting the minus 8 volts, which is what we anticipate the solution to be, which is a 2-to-1 ratio of the dependent source. So moving along to actually show you how to solve this problem by hand, because again, the simulation is great, but it's always important to enhance that experience by including into it hand solving, right? This is how you build the confidence, get way better on this. And what the idea when you have a series single loop is that I generally go 98-99% of the time clockwise notations. I include clockwise to be positive. I'm going to call it I something, but I source or IX makes the most amount of sense. And whenever you have a series circuit, the most logical thing to do to a series circuit is to do Kirchoff's Voltage Law, which means you're summing up all the voltages around this loop and they should net equal to 0. So if I put the corners on this series circuit, it's going to help me identify where my starting point, my ending point. And at least in my mind, what I have here is A, B, C, D for the corners of one series single loop problem. So if I start from A, how it's going to be read is I'm entering into that branch. It's going to be read as a negative 12. And if you've seen from my previous videos, anytime you're going clockwise, you're entering into a resistor. The resistor takes on the sign of a positive convention. So you're going to get back positive 10,000 IS plus 2Vx plus a positive 5,000 IS plus 36 volts plus Vx, all of it nets equals to 0. Okay, so that's what Kirchoff's voltage law is implying. It's that the energy in this system is entirely conserved, which is pretty cool. All right, so now we have one equation. I'm going to try to simplify that for you. So again, I'm going to put all my I source. Again, each portion here is actually a voltage, right? So the 2Vx is treated like a voltage, Vx is treated like an actual voltage, and then a resistor times it by a current is a voltage. So I'm going to just simplify this. So my 10,000 IS plus my 5,000 IS gives me the 15,000 IS. Then the 2Vx term, positive 2Vx, and the positive Vx gives me a 3Vx. And of course, a minus 12 volts and a positive 36 volts gives me a net 24 volts. So what we end up with is just one equation. Within that one equation, right, we have actually two unknowns. So something doesn't seem right, right? So one equation, two unknowns, we have to look for our constraints in our problem. And the constraint for this particular problem, I want you to think about it for a brief moment, right? So just look at the problem again and figure out what your constraint is. And when you're working with dependent sources, you're always looking for a particular constraint. So if we go ahead and copy and paste this or move this to the bottom, give you a little bit better, hopefully by now you'll recall that the constraint here is the Vx term, right? And what is Vx really equals to? And again, I'm going clockwise, so I'm entering into that positive terminal. So positive Vx is the same thing as saying 5 times it by 5,000 ohms times it by IS. All right, so it's really, really important. So this is what it's dependent on within our circuit. And again, with all dependent-based problems, there's always going to be some sort of constraint. Your objective is to find that constraint and utilize that to solve for the problem. So now that I know that it's positive Vx equals to 5,000 IS, I could either plug in Vx where I have Vx terms or solve for IS within my constraint equation and plug it in. It doesn't really matter, you get back the same solution. So again, you can either have Vx equals to 5,000 times by IS, or you can use IS equals to Vx over 5,000. It's really your call. But as you can imagine, if I'm trying to solve for IS or Vx, if I'm trying to solve for Vx first, I'm going to plug in the IS term into this and utilize that to solve. So let's see what happens when we do that. We're simply going to simplify this, right? And as we simplify this, it should hopefully leave us to one equation and one unknown, which is really our goal with this particular problem of a one loop problem. And again, when you get to two loops, you will hopefully have two equations, two unknowns, three loops, hopefully three equations and three unknowns, etc., etc. So here I am just plugging away, and hopefully you can try this yourself as you go through this. So you're going to end up with 15,000 times by Vx over 5,000. 15,000 divided by 5,000 gives me 3. So 3 Vx plus 3 Vx equals to minus 24. is my final one equation, one unknown problem, and I can get a solution for Vx, and hopefully that matches a simulation, correct? That's the whole purpose of this. So we're going to get back our Vx equals to -4, right? Which matches what we actually did before with the simulation using LTspice. And in other words, that we also can tell that therefore 2Vx is going to be 2 times that amount. So if I had -4, to be minus Vx, and if I multiply it by 2, I get back to -8 volts, which is also pretty exciting as well. We could prove that numerically too. And certainly, once we know Vx, we certainly know Is, because that is what's dependent on it. Because we based on the diagram, the problem that circuit we're given, we know that Vx will equals to 5,000 times by Is. So if I divide the -4 volts over 5,000, it gives me back the current from the source, the current of this actual loop, right? And hopefully that matches exactly what we learned from the simulation. And if you just do some quick calculations here, you'll see that indeed it does. So our value for this is going to be the 0.0008 amps, or 0.8 milliamps, right? And that's exactly what the simulation said the solution should be. So you can see how powerful this is, that you can use either or case to solve. So hopefully you found this really informative, you've learned, and you could apply this as when we go to more complicated circuits. Thanks for joining me, and I hope to see you guys. And if you enjoyed it, please thumbs up, like, and subscribe.